Hello, hello. In this lecture, in this video lecture, I will um, review some matrix algebra, show some examples in R. Specifically, I will talk about the singular value decomposition, and I will talk about how to de-mean, remove the mean of a data matrix, how to calculate pairwise distances between observations, and I will illustrate it using examples in R. So our data matrix is, we refer to it frequently as X. X has n rows and p columns. Each row is an observation. Each column is a predictor, is an independent variable, is a feature. Here's an example. This is RStudio, and if you haven't done so by now, I expect you to have downloaded R and RStudio. I will upload this. This file is available on Blackboard, and this line and this line, I just delete any objects. Here I delete any objects that are in memory, and here I clear the console. That's always something I do. Sorry. And then when you hit run, you run it on a line-by-line basis. The library ISLR is a library that has some data sets that we may use and we may play around with. And if you essentially you need to install this package, it's pretty straightforward. You go to Tools, you go to Install Packages, and then here you just type whatever package you want. ISLR install, and then that's there. Here you load it, and then one of the data sets is a caravan data set. The caravan data set the data consists of 5,822 real customer records. Each record consists of 86 variables, right? Containing socio-demographic data, product ownership, etc. So each row here is a customer. Each row of this X matrix is a customer, okay? And each column is a variable, is an independent variable, is a feature, which in this case is its social demographic data, okay? The last variable, variable 86, is purchase, indicating whether the customer purchased a caravan insurance policy or not. And when we run summary, things that we see is, first of all, if you go to this source and look at these references, you can get more information about the nature of the data. Further information on the individual variables can be obtained here. So must type, whatever that is, whatever that means, it's a number. which represents a socio-demographic variable. But if you want to know exactly what it is, you can go here, and there's more explanation. But anyway, the summary suggests that, okay, these are all quantitative variables, except the last one, which has 384 purchases and so many non-purchase. Okay, so let's just ignoring the last one, looking at the rest of the social demographic data. What I did here was to say, okay, this caravan, take all the rows. When I leave this empty, I'm saying take all the rows and take all the column 1 to dimension of caravan 2. So dimension of caravan, if you do this, it's 5,822, which is, this is your n, number of observation, and then you have these many variables. But in this case, the last variable sort of functions as a response, so we want to ignore that. So when we say caravan 2, we take this, and then when we do it -1, essentially I'm saying go from 1 to 85. Take those columns and place them into X. And then the number of rows will be n, the number of columns will be p. Okay, so that's that. Now there's another example in this data set, which is the auto. Let's look at the auto. Gas mileage, horsepower, and other information for 392 vehicles. And here's a pretty detailed description of what the different variables mean. Again, this is the source. The data set was used in 1983, and it's an old data set, but anyway, it's an example where we have 392 observations, so n is 392, and we have 9 variables. And if we are doing supervised learning, then that means that, for example, we would like to predict the mileage per gallon based on cylinders, displacement, horsepower, weight, acceleration, year, and maybe origin. Name doesn't matter. Name is just an identity. Then we will have, then P will be 8. But if we're just doing unsupervised, then we will use all the 9 variables, so P will be 9. Okay, so that's another example. Okay. Now, one thing we can do is to let's look at the rank of X, right? Let's see if it's full rank or not. Full rank meaning that the number of columns is that all the columns are linearly independent. Okay, that's what it means. Okay. So depending on whether n is greater than p or less than p, and whether x is full rank or not, there are different scenarios. But let's assume x is full rank and n is greater than p, meaning that, let's see. So there's another library which is called the Matrix library, and that has some functions which we will be using. So I will use it here, and load it here, and then I go down, and then there is this function rank of matrix X. If you look at it, the rank is 85, right? Now what is the dimension of X? X has 5,822 rows and 85 columns, and since the rank is 85, that means that all those 85 columns are pointing in different directions, and none of them can be represented as a linear combination of the rest. So X is a full rank matrix. Okay. When that's the case, then there is a decomposition called the singular value decomposition. Okay, n is greater than p, and the singular value decomposition essentially is telling us that we can write this data matrix in this very useful format, and we will use this decomposition over and over again. But for now, I just want to introduce it to you and show how we can get that decomposition in R. Okay, and the decomposition is as such. This matrix X can be written as U D V transpose, the multiplication of three matrices. Well, these three matrices have certain characteristics. The first one is that this D matrix is going to be a diagonal matrix, meaning that only its diagonal elements are non-zero and the off-diagonal elements are zero. This will play a key role later, and this singular value decomposition among many applications is useful in PCA, factor analysis, and a lot of classical methods for dimensionality reduction. Okay, so what about U and V? It's the case that the columns of U will be orthonormal. What does that mean? It means that this is U, right? It will have P columns, N rows, and the inner product of these columns is 0 if the indices, so UI transpose U2 is 0. That means that these two vectors are orthogonal to each other because the inner product is 0. At the same time, if you look at the inner product of U1 with itself or U2 with itself and so on, then those inner products will be 1. So these vectors have a length of 1 and they're orthogonal to each other. Okay, that will become also helpful. And since they're orthogonal, then U transpose U will be a diagonal matrix with 1s on the diagonal and 0 off diagonal. So essentially the identity matrix. Because U transpose will turn these column vectors into row vectors, and then you just have the inner products between any pair of these vectors, and they will be all 0 except the ones with themselves, which are the diagonal elements. Now, that does not mean that U transpose is also identity. It can be the case in certain scenarios, we'll see later, but in general, it doesn't have to be the case. Why? Because, I mean, here we have, it doesn't have to be the case. So I just wanted to draw a difference. And that's essentially mostly because of n being greater or equal to p. If n is equal to p and x is full rank, then yes, this happens. But otherwise it doesn't. At the same time, well, let's just go to R for a second. And pause here and look at this. Let's see what I mean. Okay. So we have this matrix, do this, and here we run SVDX. So that calls a function in R which does a singular value decomposition of this matrix X. And then to get the diagonal elements, so this SVDX object has 3. So U is a matrix U, V is a matrix V, and D is a vector. And these are just the diagonal elements of D. So I'm just calling them, and then I call the function diagonal to create a diagonal matrix. Now D is a diagonal matrix. It's huge. but you see on the diagonal elements are these values placed from largest eigenvalue, singular. These elements are called the singular values, from largest to smallest. Okay, and then if you remember PCA, you would pick the largest ones, and then you would project everything on the first 2 or 3 largest one. But let's just keep that later. I'm talking about. I will talk about that later. Okay, so that's D. Then we call U, and then we call V. Okay, so you have U, and then we have V. Okay. Now, inner product. So U, right? Let's say we take the first column. If you want to look at the inner product between these of the inner first column with itself, then we do T around this, which means the transpose, and in R, it's this which does the multiplication between vectors and matrices. And we get 1, you see? So the inner product between these two vectors is 1. If you look at 2, it's 1. But if you look at between 1 and 2, it's 0. Well, it's 10 to the power of -6, and that's the precision of the machine. So for us, that's 0. If you look 2 and 10, it's 0. If you look 2 and 20, it's 0. If you look 10 and 10, it's 1. Okay, so that's what we meant by what we said when we said the columns are orthonormal, meaning that the inner product between any two is 0, except for those that you're looking at the inner product between the vector and itself. Okay, so you get this matrix. Now let's look at that again. If you look at TU, which is U transpose multiplied by U, you get this huge matrix, which is hard to look at, but just look at these elements. The 1, 1 element is 1, the 2, 2 element is 2, the 3, T element is 2, and then the rest, the off diagonal, are in the order of 10 to the power of -15, -16. So technically these are 0, right? Which is what we had here. Now what I meant by U transpose not being identity, let's look at it. It's going to be a larger matrix. It's going to be a 5822 matrix, and let's actually look at this. That's easy. Let's put it into a matrix A, and then we can look at A11, A12, A13, A14. So it's just the first 10 elements. So you see, it's not like that the first element is 1 and the rest are 10 to the power of -15. This is not the identity matrix. Okay. Now let's come to V transpose. V transpose is going to be a square matrix. And the rows are going to be vectors that are orthonormal. So essentially the columns of V are orthonormal. But since this is a square matrix, and so again, Vi transpose Vj is 0 if they're not equal, and it's 1 if they're equal. But since this is a square matrix, V transpose V is I, but the other way around is also correct. V transpose is also identity in this case. So let's look at it. No, just look. So we have the same thing here. Right. Then we look at this, it's 1. Now, so V transpose V, again, 1 on the diagonal. And the off-diagonal elements are of the order of 10 to the power of negative 16, 17. Sorry. Okay. So that's that. Now, V transpose V in this case, sorry, V transpose is also going to be a diagonal identity matrix. One, and then you have these off diagonals are very small, diagonal elements are around 1. Okay. Now, why do we care about this orthogonality? We'll talk about that later, but let's just look at this. And the reason is just I want to show you a few important things. This diagonal matrix, D, is useful because D square is cheap to calculate. Squaring a matrix is a computationally, I mean, not very heavy, but it's not it takes a lot of operations because you have to inner product any row with its own, a bit different rows. So you have to calculate all the pairwise inner products between the rows. But when you have a diagonal matrix, all you need to do is square the diagonal elements. Or if you want to look at the inverse of a diagonal, you just have to look at the inverse of the diagonal elements. Assuming there are non-zero, it's pretty straightforward. But inverting a matrix is a computationally intensive task. So that's why we like decompositions which involve matrices with orthonormal rows or columns, and diagonal matrices. And here's an example. X. We learned that the singular value decomposition allows us to write X as U D V transpose. Now, if we look at X transpose X, then we have these three matrices. We look at the transpose, and then we have these three. Now the transpose of this tree will be the transpose of V transpose, the transpose of D, the transpose of U. And then you have U, D, V. Now U transpose U is identity, as we saw before. And the transpose of the transpose is the matrix itself, as we saw before. So we end up with V, D transpose, I, D, V transpose. Identity multiplied by any matrix gives us the matrix itself. So we'll end up with V, D transpose, D, V transpose. And since D is a diagonal matrix, right, the transpose of it is itself. It's a symmetric matrix, essentially. So the transpose will be D itself. So you have V, D square, V transpose. Okay. Now, why is this useful? So we wrote X transpose X as V, D square, V transpose. It's useful because now if we want to compute the inverse of this matrix, we can show that the inverse is just V, D square to the power of negative 2 V transpose. So all we need to invert is the diagonal element. The rest is the same. Where d to the power of negative 2 is easy to calculate. Just 1 d1 squared, 1 d2 squared to 1 dp squared. Okay, now what comes next, I want to show you, and in a sense, show you that this is essentially the inverse, and to show that we have to multiply this by this matrix and see that this gives us identity. So x transpose x inverse x transpose x. So x transpose x inverse we claim is v d inverse d to the power of negative 2 v transpose. It's here. X transpose x is v d square v transpose. V transpose v is identity. D inverse d to the power of negative 2 times d to the power of 2 is identity again. And v transpose is identity. Remember? In this scenario where n is greater than p, imagine everything here we're doing is based on this assumption. N greater than p, and x being full rank. Other scenarios, I will consider the other case too, but for now, just remember everything we're saying is for n being greater than p. So x is a tall matrix. A lot of modern data sets, x is not anymore tall, it's a wide matrix, or near wide matrix. It's classical data sets look at very thin, tall data sets, but modern data sets where we have a lot of data, we have a lot of independent variables. A lot of them might be totally irrelevant, but we have them nevertheless, and we do not know. We know a small subset of them are relevant, but we don't know which. So we will include them. And those extra features make our matrices wide, where p can be greater than n. And when p becomes greater than n, then we need a different look, and some different new phenomena will arise that we will talk later. But for now, remember, everything we're saying is for n being greater than p, or equal, but mostly n greater than p. So x is a tall matrix. And for such a matrix, VV transpose is identity, okay? And we saw that. Now, for X transpose, for a matrix to be an inverse, it should give us identity both when we multiplied from the left and from the right. So let's check the right, if we multiplied from the right. X transpose X was V D square V transpose. And X transpose X inverse we claimed is V D to the power of negative 2 V transpose. Again, V transpose V is identity, D to the power of 2 times D to the power of negative 2 is identity, and VV transpose is identity. So yes, that's why we like this singular value decomposition. It's one of the key computational steps. When you have the singular value decomposition of your data matrix, then you can do many things with little extra computational effort. That's why singular value decomposition is computationally expensive, because once you have it, the inverse, you also have the inverse. You don't need to spend a lot of computation to get the inverse. You just need to invert the diagonal elements of D, or D squared, sorry, which is pretty straightforward, as opposed to inverting a matrix, which is complicated. Okay. So this is just a little bit linear algebra, single value decomposition. And if you want a reference in a textbook, let me just show you something. So this book, Deep Learning, if you just Google it, the PDF is available for free in the public domain. And even though the subject is not deep learning, it has a very useful first chapter, and it's in the public domain. It does a reasonable job in doing a lot of exposition of linear algebra in a short amount of, like in almost 20 pages. Okay. Now what we talked about, if you just were interested to look a little bit further, single value decomposition, and essentially this is what we did. UDV. The A here is our X, and we have UDV, and you can take a look here. Okay, another book that might be useful for some of you, again, it's available for free in the public domain, is this book. And if, for example, it's things that I so far spoke about is the inner product. Again, here you can look at it, and let's see. Linear dependence. This is a chapter when we talked about linearly independent vector or dependent vector, orthonormal vectors. If there's still something that's not clear, you can take a look at these few pages and examples. So my objective is just to cover enough so that everybody understands the topics without going too deep into it, and leaving the references, so if you want to go a little bit deeper on your own, to have some place to do so. Okay? All right, so that's that. Now, let's go back here. Oh, another book that I didn't put in the syllabus, because there are so many books, and it's not directly related to what we do, but it's available for free in the public domain, and it's this book. And the reason I wanted to share it with you, one was it's available for free in the public domain, and then okay, no, never mind. I thought that the appendix has a good linear algebra section, which it doesn't. Okay, never mind. Okay, next thing I want to talk is about correlation matrix. Okay, and how do we find the correlation matrix? What does it mean to find the correlation? What is the geometric interpretation? Okay, coming back to our data matrix has n rows, p columns, and each row represents an individual or an item. In the two examples we saw, the individual was, that was an individual regarding the caravans. And the auto example, each row is a car. Okay, so it's an item, an object, or an individual. That's what they mean by data point. Okay, So mu is a vector which is calculated by summing all the rows and taking an average. So it's a mean. It's a mean vector. It's a sample mean. So maybe I shouldn't call it mu, but never mind that. And in R, if you want to find this, if you want to create a vector, essentially column means this command creates that vector for you. So it finds the means along the columns. And then if you want to place it into a column vector, then you use the command matrix. So you have these numbers, and then you want to place it in the p by 1 matrix, which is a p by 1 vector. Sometimes we like to have a vector which is filled with ones. And let's call it just capital capital 1. And again, here we can use the function rep 1n, so repeat 1 n times, and then place it into an n by 1 matrix. Okay. Now, why do we care about these two? Because if you look at the 1 mu transpose, so you have this 1 vector, which is an n by 1 column vector, and then you have mu transpose, which is this row vector, 1 by p, then you end up with an n by p matrix, where each row is filled with mu transpose. Essentially, that's what it is. So this 1 is multiplied by mu1, goes here. This 1 is multiplied by mu2, goes next to it. This 1 is multiplied by mu3, goes next to it, and so on. And then you do repeat that, n by p. Okay. Now, if you have this data matrix and we subtract 1 mu transpose, we get these rows, these lines, these horizontal lines are there to say, okay, this is a row vector. And of course, in our notation, every vector is a column vector, so the transpose of it makes it a row vector. So x minus 1 mu transpose is the rows of x with the mean subtracted. Okay, with the means subtracted. So we can call it a d-meaned data matrix. Okay, and this is how we write it in the matrix vector notation. Now, if we take the transpose of the d-mean matrix, so these rows will become columns. Okay, and then you take this and multiply it by x minus 1 mu transpose, so you have the inner product between these. So here will be the inner product between 1, x1 minus mu transpose, x1 minus mu. And then this will be the inner product of x1 minus mu transpose, x2. Then you have the inner product of x1 minus mu transpose times x3 minus mu. And so on, you go to the end, you have, so this is the first row, x1 minus mu transpose, xn minus mu. The diagonal elements will be just inner products with the vectors themselves. So essentially, if we call this matrix A for simplicity, the element in the ith row and the jth column is just the inner product of the features of the ith observation, ith item, ith object, ith individual, inner product with the jth individual. Of course, D mean, so we subtracted the mean, and then we're looking just at the inner product between the features of the ith individual and the jth individual. So why is inner product so, why do we care about inner product? What does inner product stand for? What can it represent? Yeah, why? Okay. That's the reason. If A is a vector and B is another vector, A transpose B, we can show it's an inner product, and it's just the length of A, the vector A. So inner products are scalars. So the length of A is the physical length of this vector. This is the L2 norm. Then we have the L2 norm of the B vector times the cosine of the angle between. So in a way, inner product heavily depends on the angle between these two vectors. What does the angle tell us? Well, if two vectors are orthogonal, the cosine is 0. If two vectors are pointing exactly in the same direction, the cosine is 1. And if they're pointing in totally opposite directions, it's -1. So the cosine is a number between -1 and 1, and the closer it is to 1, the more the vectors are pointing in the same direction. And if they're pointing in the same direction, then maybe they're expressing the same pattern. But that's why we like to see the angle, the cosine of the angle between the two vectors, the two individuals, the two objects, the two data points. And then maybe if we find data points which are more or less pointing in the same direction, maybe that's something useful for clustering them. Then we can say, okay, this group of data points, they are more or less pointing in this direction, and this cluster is pointing in this direction. So this is all going to be useful in clustering and dimensionality reduction later. Okay, so just a reminder, or just to repeat something we said before, the L2 norm is the square root of the squares of the individual elements of A. So that's the physical, that's the L2 norm. Okay. Okay. So the cosine of the angle between A and B the cosine of the angle between A and B, so we can divide both sides by the norm of A and the norm of B, right? Then we have the cosine of theta is A transpose B divided by norm of A, norm of B. Okay. So let's imagine we want to find the cosine of the angle between the individual items, objects, or or people. Okay. So on the one hand, for individual I, we have the d-mean feature vector of xi minus mu, and then we have xj minus mu, and then we have the angle between them, which is theta ij. So theta, the cosine of theta ij is just the inner product of xi minus mu transpose xj minus mu. Divided by the L2 norm of xi minus mu and xj minus mu. It's just essentially what we have here. I'm just applying it specifically. So this becomes A, this becomes B, and this becomes the angle between these two. So the L2 norm is just the square root of the inner product. And the L2 norm of xj minus mu is also the square root of the inner products. Now, look at this. Imagine x bar. Let's x bar, I just, for the sake of simplicity of notation, we define it as x minus 1 mu transpose. So it's a d-meaned version of x. So it's x, each row of x represents an individual item or observation. And then imagine that among all the data points, we have a mean for each independent variable. We subtract that. So that we call it x bar. It's different from the sample mean. So the sample mean that's been used, x bar is also being used for that. But here, since we explicitly make it clear what we mean by x bar, so I hope you don't make that mistake of mixing these two. So x bar here is what I defined here, is the d mean of x. So x bar transpose x bar, the diagonal elements are just the L2 norm of x1 minus mu, the L2 norm of x2 minus mu, the L2 norm of x3 minus mu, and so on. Okay, so let's create a vector sigma, which is a vector of n elements, sigma. Okay, so I think here there's a maybe there is a mistake here. 1 second. No, it's all okay. Yeah, it's all okay. So sigma, and sigma I is just the square root of xi minus mu transpose xi minus mu. Okay. Why do we care about this? Because didn't we want these terms here? We have the inner product, right? Xi minus mu transpose xi minus mu. We have it here. And we had it here. You know, this is x bar transpose x bar. We had it here. Now we just have to divide them by the norm of each term to get the cosine. Okay. So sigma transpose is, sigma is this column vector, sigma transpose is this row vector. So sigma transpose is sigma 1, sigma 1, sigma 1 squared, sigma 1, sigma 2, sigma 1, sigma 3, to sigma 1, sigma n. That's the first row. Second row is sigma 2, sigma 1, sigma 2 squared, sigma 2, sigma n. And then you have sigma n, sigma 1 comes here, sigma n, sigma 2. Okay, this is a mistake. This is supposed to be sigma n, sigma 2. This is supposed to be sigma n, sigma 2, and so on. Okay. So in R, so now what we have is we want to we want to find these cosines. So we have these elements here. We have to divide them by these elements, element-wise. And in R, A is backslash, B is element-wise division. Okay, so if A is a square matrix and B is a square matrix, then A backslash B, or slash, I don't remember which one was back, which one was the normal one. It's just element-wise division. It's not matrix inverse. Okay, so essentially, if x bar is x minus 1 mu transpose, just if it's becoming confusing, just pause, go back to your notes, make sure every step. And in this lecture, in this video lecture, all the steps were covered. If it's confusing, you just need to pause, go back to your notes, repeat everything that I've written, transfer it in a piece of paper for yourself, and then it'll become clear. So in R, if we calculate x bar transpose x bar divided by excuse me, by sigma transpose, then we get the cosine of the angles between the data points. And then we have the pairwise cosines, which can itself be a measure of distance, or the opposite of a distance. Essentially, when it's 0, then the two vectors are pointing in orthogonal directions, where theta ij is the angle between these two. Now, once you have this, this matrix can be the factor of. It's being used as an input to many clustering dimensionality reduction algorithms, from PCA to factor analysis to spectral clustering, and I will use it. I will use it. But for now, I think this is sufficient. I don't want to overwhelm you. This is all mostly notation, but I think it's a language that if you become comfortable, it will open many doors, and it will give you the feeling of confidence, as opposed to just being overwhelmed when in reality it's nothing really overwhelming. It's just a different language. Okay. Now, how do we do this in R? It's pretty straightforward. This is our I1s is our vector filled with ones. This is our vector of the means. And then here I'm just saying x. Let's just write it as this x is just this one. What do we have here? Just remove this. Okay, so this is just x bar transpose x bar. Then we take the diagonal elements of this matrix. Okay, so this is just x bar transpose x bar. And okay, and then we take the diagonal elements, we take the square root, we put it into p, should be p by 1, or let's see, maybe we are doing something wrong here. Let me just take a look back. So ones is n by 1, mu is 1 by p, okay? N by 1, 1 by p, that's correct. And the diagonal elements, so x is n by p. So, oh, then the sigma matrix will be p by p. So maybe I made a mistake here. Let me see. Did I? No, I didn't. So then let's just run this from the beginning. Okay, so the theme of x bar t x bar is 85. P is 85. Oh, okay. Now I know what was the... No, this is... yeah, okay. Now I know what's the mistake. This transpose should be here. There should be a transpose here. Okay, so just the order of the transpose should be different. And let me just correct that. Now I know what was wrong. It should be the other way around. Okay. Just make it red so everybody sees. Okay. Okay, so you see this one, it needs to be, the transpose should be here. I corrected it there. I corrected it here. And also here. Okay. So okay. So this is just essentially transpose differently. Oh, okay, this should be n, sorry. Okay, let's do it from the beginning. Just okay. So now we have this correlation X, which is a huge matrix because we are looking at the pairwise correlation between different, in this one it's the chiral one. Insurance company data set between the 5,822 individuals, and obviously the correlation of everybody with themselves is 1, and then it becomes 0.57 negative. So, and then this can be the basis, as I said, of many dimensionality reduction clustering algorithms, this distance. Okay, so this is just an introduction to linear algebra. exploratory data analysis, and dimensionality reduction, essentially. All right.